Namaste. In this video, we are going to discuss about non-deterministic automata with lambda transitions. Lambda transition. Lambda transition is nothing but on reading the empty string where the control will be in. So in this example, if you see Q0 on reading A, it will be in Q1 and also Q2. It is not Q1 and also Q2. It is Q0 on reading A, it will reach Q2 directly. That is the concept of lambda transition, where without reading any string, it will move to the next state. We'll see how it will work. The input is AA. So as usual, I'll start from the initial state. So Q0 on reading A, I will reach Q1. Read head does not move. That is, input will not be read. It will directly go to Q2. And for the next A, it will reach Q3. So the language accepted by this automata is AA. So all input is consumed. And because I have reached the final state, the input AA is accepted by the automata. So this automata is non-deterministic finite automata with lambda transition. Also we can say epsilon NFA or lambda NFA. We'll see a rejection example. AAA, where on reading first A, Q1, then Q2, and reading the second A, Q3. But one more element is there which has to be consumed, but there is no transition. So this string is rejected by the epsilon NFA. Next, what is the language of this? As I already told, the language accepted by this automata is AA. Another example we'll see. So what is the language of this? If we see, again it is accepting A, B is accepted. Then again it will go on moving as I have Q2. After reaching Q2, it will go to Q3, again Q0 without reading any inputs. Again it will read AB. We'll see that on reading A, control will be in Q1. On reading B, control will be in Q2 and Q3, and it will come to Q0 without reading any inputs. Then again it will read A, again it will read B, accepted. So the language accepted by this automata is AB, and AB repeatedly it can come any number of times. So in short, how we can represent this is AB to the power plus. This plus represents AB can come any number of times, but 0 cannot be there. It means AB at least once it should come, and that can be concatenated with any number of ABs. That is the meaning of this plus. This plus is also called as positive closure. Another example we'll see. Here if you see, the language accepted by the automata is, because the initial state itself is the final state, it will accept epsilon, and then on reading 1, 0, I can reach the final state, and I can read any number of 1 zeros, so that will come as the language. Then this 0, 1, this Q2 is nothing but a trap state, because from trap state, that from Q0 you cannot move to any other states, so this Q2 is a trap state. So how I can write is 1, 0 can come any number of times because it will accept lambda also. The language can be represented as 1, 0 to the power star closure. Star closure means it will read empty string also. The lambda symbol never appears on the input tape. Input tape we will not have. So this you have to keep in mind. Simple automata languages. So the language of accepted by this automata is null set M1, and the language accepted by this automata is empty string epsilon or lambda. So this is the language accepted by, that is empty set, and this is lambda. Lambda transition in deterministic automata. NFAs are interesting because we can express languages easier than finite automata. Yes, languages are easy to express in NFA. Why? Because for every input symbol, I need not have a transition. But in DFA, we have to concentrate on all the input symbols. We have to decide what will be the next state. So in this example, if we see, on reading a single A, I'll be reaching Q1. After that, if I read any number of A's, it will go to the trap state. So this is a deterministic finite automata. So the same thing, how I can write in a NFA is, I can have only one transition. So it will reject null set, or else it will reject any number of A's. It will accept only single A's. So this is the deterministic automata and this is the NFA, which is easy to construct. So the formal definition of NFA, again the same thing, Q set of finite states. This is the sigma input alphabet and the transition function, initial state, accepting states. Everything is same, similar to the DFA, only changes with respect to the transition function, where on reading a single input, I can have more than one state. So how I can write the transition function? Q0 on reading 1, I can reach Q1, and Q1 on reading 0, I can reach Q0 also, Q2 also. And on reading lambda, I will be reaching Q0 and also Q2. And Q2 on reading 1, there is no transition. So as we have already seen extended transition, the same thing here also we'll see. Q0 on A, I can reach Q1. And Q0 on AA, I can reach 2 states, Q4, Q5. And Q0 on reading AB, I can reach 3 states, Q2, Q3 and also Q0. So formally how we can represent this is, there is a walk from Q1 to Qj with the label W. This definition we have already seen for DFA. The same thing, but only differences with respect to the transition function, where I can have more than one state on reading the same input symbol. So for this, can we tell what is the language accepted by this automata? So definitely, because initial state is the final state, it will accept lambda. Then it will accept AB any number of times, and also it will accept AA. So the language accepted will be, so they will see that. Before that, we'll see the extended transition function. If it is AA, it is Q4, Q5, so that is accepted. Next AB, it is accepted. Next AB, AA, yes, of course it is accepted. Next ABA, not accepted. So it is nothing but lambda union AB any number of times concatenated with AA. So this is the language accepted by the epsilon NFA or NFA with lambda transition. So formally how I can define the language is that language accepted by this automata is nothing but Q0 on reading the string, I have to reach the accepting state, at least one. So this is the representation. On reading the string, I can I will have more, I can reach any number of states. In that, at least one state should be final state. Thank you.